Alright, hey everyone, we're back with more momentum. Today we're going to look at the conservation of momentum, which is kind of like a tricky, sort of interesting topic. We're just going to do a little bit with it, kind of show you guys what it is, what it's about, and what you can do with it. And that'll be good. So, conservation of momentum. Momentum is, we already talked about it, it's this sort of like quantity of motion. It's the amount of motion that an object or a system, which is just a couple of objects, has. And momentum is what we call conserved, which hopefully sounds like a little bit familiar from our energy topic. Energy is also something that is conserved. And what being conserved means, it means like if a system, meaning a group of objects, has a certain amount of this thing, it'll always have that. Like, remember we did energy? Like, if an object has a bunch of energy at the top of its path and it falls, the energy changes form, but it's still all there. Conservation momentum is kind of the same thing. If a system has a certain amount of momentum and something happens, when we talk about momentum, it's typically like collisions or explosions, like objects pushing off of one another. If there's a certain amount of momentum and something happens, the amount of momentum afterwards will be the same. We call that the conservation of momentum. So to put this into words here, the total momentum of a closed system is constant. The total momentum of a closed system is constant. So what I mean by constant is it just has the same value before and after, like a collision or something like that would happen. When I say a closed system, that means that there's no outside forces. So we kind of have to isolate the system in order to see that. Outside forces can sort of like mess around with all of the things that are going on. So this really works best in a closed system where there's nothing interfering with what's happening. So the total momentum of a closed system is constant. The way that kind of works is essentially if you've got multiple objects, which would be our system, like two cars that collide or something like that. Basically what happens there is any momentum lost by one object is gained by the other. And that's sort of how it's conserved. It's like if you give someone like some money or something like that, right? So there's you and your friend, you give them some money. All that money is like conserved, meaning it's all still there between the two of you. You lost some of that money because you gave it away. Your friend gained some money because that's who you gave it to. But in all, the total money is still there between you. It's conserved. And momentum's kind of the same way. So if there's a collision and one object loses some momentum, then the other one will gain some momentum. And that trade-off means that it's all still there. It's all still between the two objects. It just transferred from one to the other. And again, the word we have for that is conserved. So just momentum is conserved. That's what I mean by that. And we use this when we talk about collisions, so two objects crashing into one another, and we'll go over how we do that in a couple minutes. Used for collisions or explosions. And explosions is not quite as cool as it sounds. It can mean actual explosions, but typically it's just objects pushing off of one another. They're said to explode off of one another. It's the word we use for that in physics. So not quite as cool as it sounds. But there is an equation for this, although we're more or less just going to think our way through it. But the equation looks something like this. P before equals P after. So when I say P before equals P after, remember P stands for momentum. P before equals P after means that the momentum before something happens, like before two objects collide, is equal to the total momentum after the two objects collide. So all the momentum is conserved. It's all still there. It just might have gone from this object to that object, but again, the total momentum is still there. Last little thing to add before we start trying a couple of these problems is sign convention. So momentum can be positive or negative depending on the direction that you're moving. And because it's what we call a vector, which means it has a direction. We're not going to dive too far into this, but here's what we'll do. Let's just say that, for the sake of all of these problems, anything moving to the right will have positive momentum, and anything moving to the left will have negative momentum. So things moving to the right have positive momentum, things moving to the left have negative momentum. And the reason we're doing this is that way we can use positive and negative answers to help us figure out which way an object is moving. Is it moving to the right or to the left? And, the sign of our answer will tell us that, actually, which is kind of neat. Let's try a couple. So again, we're going to do 12, 13, and 14 together. Then I'll pause and have you try 15, 16, 17 on your own, and we'll see how it goes. 12. A white cue ball is traveling. So if you ever played pool, the cue ball is the white ball that you actually hit with the stick. So a white cue ball is traveling with a momentum of 10 kilogram meter per second and collides with the black 8 ball, which is at rest. After the collision, the cue ball has a momentum of 3 kilogram meter per second. What is the momentum of the 8 ball? So we have a collision, and in physics, when we see collisions, we do the conservation of momentum. It's like the tool that helps us with this. And the conservation of momentum says this: the total momentum before two objects collide is equal to the total momentum after they collide. So, what I'm going to encourage you to do, though, is to kind of think about it. We have this drawing that's really going to help us out here. A white cue ball is traveling with a momentum of 10 kilogram meter per second. So I'm just going to give this a plus 10, because that's the momentum that it has. I made it positive because which way is it traveling? Well, to the right. To the right is positive. And good. So for the black 8 ball, it collides with the black 8 ball, which is at rest. If something's at rest, it has a momentum of 0. Let's pause and think about our momentums. We've got a momentum of plus 10, a momentum of 0. What's the momentum of the system, meaning both objects combined? Well, 10 and 0 makes 10. Now let's talk about after. After the collision, the cue ball has a momentum of positive 3. So positive 3, which means it's moving, that way still. Notice it has less momentum, so it's slowed down, which kind of makes sense. If you're moving and you crash into something, it'll probably slow you down. What's the momentum of the 8 ball? Let's think about this. Initially, we have a total momentum of 10, because 10 and 0 make 10. Which means that afterwards we have to have a total momentum of 10 still, because it's conserved. The total momentum still has to be there. So if 3 are on this object, then the other one must have 7 kilogram meters per second. And that's our answer. And again, here's how we did that. We have a total momentum of 10 before, which means we have to have a total momentum of 10 afterwards. 3 and 7 make that 10. And so that's it. Momentum is conserved. And this helps us figure out what this, the 8 ball is doing, so we can calculate, if we had more information, how fast it's moving, which way it's moving, and all of these things. But for now, this is good. Alright, 13. A car is traveling to the right with a momentum of 8,000 kilogram meter per second, when it collides with a van traveling to the left with a momentum of negative 12,000 kilogram meter per second. So I've got a car, it's traveling to the right, and it has a momentum of 8,000. I'm going to make it positive 8,000 because it says it's to the right, and I made it positive. And then the van is moving to the left, and notice that it has a negative momentum because it's moving leftwards of negative 12,000. Alright, after they collide, what's their total momentum? Well, after they collide, the total momentum has to be the same as before they collide. So let's find that total momentum, and that's our answer. Plus 8,000 minus 12,000. Well, plus 8 minus 12 is, I think, negative 4,000. And that's it. That's your answer. That's the total momentum after they collide. And again, if we wanted to dive deeper, we could figure out how fast they're moving based on that and all of these other things, but for now, that's pretty good. Why is that helpful? Why do we care? Well, look at B. In what direction will they travel after they collide? Well, we got a negative answer. And negative means, I think we agreed before, negative means left. So now we know which way they'll go when they collide. It's a helpful piece of information. So kind of what that means is the dominant momentum is towards the left, and after they collide, they're going to move towards the left, because left is negative. That's good. 14. A cannon is initially at rest. It fires a cannonball with a momentum of 300 kilogram per second. I want to know, what is the recoil momentum of the cannon? Okay, so let's look at what recoil is first. Recoil is, if you take like a cannon, so this, oh god, this is going to be our cannon. Yeah, and it shoots a cannonball. The cannonball goes forwards, and the cannon does what's called recoil in the backwards direction. So what it looks like is kind of something like this. So there you have an example of recoil. You have this cannon fires a projectile forwards, and the cannon, as a result, gets kicked backwards. Again, the word we have for that is recoil. Shown a little bit more clearly, but with less people getting hurt, so I guess it's less music, is this one right here. So this cannon is going to fire an object forwards, and when it does, the cannon recoils backwards. So again, you can see the cannon kind of jump backwards because it fired an object forwards. The word for that is recoil. So if we go back to this, I want to know what's the recoil momentum of the cannon. To do that, let's think of this. A cannon is initially at rest. So at the beginning, what's the total starting momentum? Meaning P before. Well, P before, if everything's at rest, you have a loaded cannon, it's just sitting there. What's its momentum? Well, if nothing's moving, it should be 0. Now what that means is our total momentum afterwards must be 0. So if we fire the cannonball forwards with, if we fire the ball forwards with 300 momentum, positive 300, again the total has to be 0 because it has to equal the before. Alright, well if one moves forwards with 300, then the other one must move backwards with negative 300. Why does that make sense? Well, if one's got, think about our numbers, plus 300, minus 300, what's that equal to? I think it's equal to 0. The momentum was conserved. It's the same before and after. So to answer our question, it's negative 300. Because again, it still has to balance out to equal 0. So all the momentum that you give forwards is equal to all the momentum backwards. Alright, we got a negative answer, which means that which way will the cannon be moving? To the left, or backwards, because it got a negative momentum. Cool. If the cannon has a mass of 100 kilograms, how fast will it be moving? How fast will it be moving? So that's the velocity I think we're solving for. And we're going to have to go back to our older equations, meaning from a couple days ago. And if you forgot them, they're all the way in the back of your packet. We're solving for the speed or velocity, so I'm going to use this guy right here. The v equals p over m. So the cannon, v equals p over m. Its momentum was, I think we said it was negative 300 over a mass of, I think the mass was 100, because I told you that right here. Alright, negative 300 divided by 100 is negative 3 meters per second. We got a negative velocity, but that's okay, because the velocity is just how fast you're moving. And which way is the cannon moving? To the left or backwards. So that negative answer actually makes a lot of sense for us. Alright, this is kind of a weird idea. I know it's a little tough, but I want you to pause the video and try 15, 16, and 17. If you're having trouble with them, just skip it, go to the rest, and then resume the video whenever you're ready. During a football game, a running back is moving to the right with a momentum of 500 kilogram meters per second, collides with a linebacker moving to the left with a momentum of negative 400 kilogram meters per second. Alright, I like the drawings because they help me out. So we've got our, what was this, a running back moving forwards at 500. Let's give it positive because we're moving to the right. And then we have a linebacker going the other way. Give him some arms and a happy face. He's going this way with negative 400. Ran out of space for my units there. Alright, after they collide, what's their total momentum? So after they collide, the total momentum is the same as before they collide. So before they collide, we got plus 500 minus 400. Plus 5 minus 4, I think that's positive 100 kilogram meter per second. Cool, awesome. We got a positive answer. Which way is positive? I think it was to the right. Awesome, so we know which way they'll move. So in a football play, that's the idea, right? These two players collide, and if you're on offense, if you're the running back, you want that total momentum to be in the forward direction. That way, after you get hit, you'll sort of like continue moving forwards in the end. Cool, that's it. 16. Two ice skaters begin a rest facing one another, as shown in the diagram to the right. Alright, we've got the masses here. We're just standing there facing one another. When both skaters are at rest, what's the total momentum? Well, if everyone's at rest, the total momentum would be nothing. If nothing's moving, there is no momentum. There's no motion in our system. That's it. Right. For B, the two skaters push off one another. 50 kilograms is going to move to the right. So she's going to move to the right. He's going to move to the left. The 50 kilogram skater moves to the right with a momentum of plus 200. Now that plus 200 is the momentum, not the mass. So I know there's a couple numbers here. This is the momentum. What is the momentum of the 100 kilogram skater? So what does this guy move to the left with? To do this, that's the conservation of momentum. Before they separate, we have a total of 0. That's this right here. Which means after they separate, they need to still have a momentum of 0. How can you do that? Like, how can you have plus 200 but still have a total of 0? Well, I think that makes sense if the other person has a momentum of minus 200. Again, which just kind of means 200 but backwards. Plus 200 minus 200, that's 0. So that's how this all comes together. So I got negative 200 kilogram meter per second. Negative means which way does he move? To the left. And that's all that negative really means here. Cool. Alright, what's the speed of the 50 kilogram? And then for part D, I'm going to ask for the speed of the 100 kilogram. So I'm asking for both of those because I want us to compare the two in the end. Well, we have an equation for speed. I'm going to jump down to my equations on the last page, and it's the circled one right here. The one I think we used it earlier, that's why it's circled. V equals P over M. Alright, so I want the speed of the 50 kilograms. So V equals P over M. P for the 50 kilogram, the momentum was, I think this 200 right here. The mass was 50. Alright, 200 divided by 50 is 4 meters per second. So she moves to the right with a speed of 4 meters per second. Let's check part D, and then we'll think about our two answers. Part D, I'm asking for the same thing, but I'm asking for the other object, meaning the 100 kilogram person. So I think his momentum was negative 200. Negative 200. Looks like just a happy face there. Over a mass of 100 kilograms. 200 over 100 is 2. I think you may get negative 2, though, if you made this momentum negative. Negative just means backwards. And here's why I asked those two questions. The person moving to the right is 4 meters per second. The person moving left is 2 meters per second. Which one's moving faster? Well, the girl, the 50 kilogram skater. Why are they moving faster? Well, they're moving faster because they're lighter. That's it. This person has half the mass and actually moves twice as fast as a result of this. This person is twice as heavy and will move at half the speed. So the heavier you are, the slower you'll move. Which kind of makes sense, because big, heavy objects are hard to push. They're hard to move, so it'll move a little bit more slowly. Last up, Granny and Ambrose. That's kind of a weird question, but whatever. Granny whizzes around the rink with a momentum of 240 kilogram meter per second, and is suddenly confronted with Ambrose at rest, directly in her path. Rather than knock him over, she picks him up, and continues in motion without braking. So here we've got Granny moving to the right, with a momentum of 240 kilogram meter per second. And this little guy is Ambrose. He's at rest, so his momentum is 0. Okay, so this is before they collide, 240 and 0. Let's answer the question now. For part A, what's the total momentum together after they collide? Well, it has to be the same as before they collide. And before they collide, we have 240 and 0 makes 240. And that's it. Momentum's conserved. So if before you've got 240, then afterwards we have 240. The difference here is that beforehand, it's kind of split up amongst these two separate objects. I know it's not really split up because one has 0. But then afterwards, we just combine the two objects together, which means that there's just one combined object with one combined momentum. So for B, if Granny and Ambrose have a combined mass of 120 kilograms, what's their speed? So we can use momentum to calculate their speed. And we're going to do that. I'm not going to go back and look up the equation at the last page because we did that a couple times already. But it's that same equation. I think you have a momentum of 240 kilograms and a mass of 120. 240 over 120 is, I believe, 2 meters per second. And that's it. Alright, I know this was tricky, but we'll do some practice with it, and we're not really going to get too far into the weeds with this particular topic. If you have questions, come to my office hours or just email me, and I'm happy to answer.